Hello everyone, welcome back. In today's lecture, we are going to study one of the most important chapters in the structure of an atom, filling of electrons in different orbitals and electronic configuration of elements. Now, at first glance, this topic may seem like it's all about memorizing electronic configurations, but that's not true. But at the end of the chapter, you'll understand why electrons occupy certain orbitals first, why some elements behave differently from others, and even why the periodic table is arranged the way it is. So instead of memorizing, let's understand the logic behind it. So let's start with a simple question. We already know that an atom consists of three fundamental particles, protons, neutrons, electrons. Protons and neutrons are present inside the nucleus, while the electrons are found outside the nucleus. But here's an interesting question. Are electrons moving randomly around the nucleus? The answer is no. Electrons are most likely to be found only in certain specific regions around the nucleus. As you can see, orbitals. The thing is, an orbital is defined as the region, the space around the nucleus where the probability of finding an electron is maximum. You notice the word probability? It doesn't mean the electron fixed at a point, it's gonna be there. But it has the highest probability of being there. We are not trying to find a fixed point. Instead, it means that we are trying to locate the electron many times. We are most likely to find it in a particular region. Now, often we get confused between shells, subshells, and orbitals. Let's understand the difference. The shells are represented by K, L, M or N, or numerically as N is equal to 1, 2, 3 and 4. Inside every shell, there are one or more subshells. These subshells are represented by the letters S, P, D and F. Finally, each subshell contains one or more orbitals. So, the hierarchy is very simple. Shell, subshell, then orbital. Here you can see the actual definitions of all three. Now, think of it like this. Imagine a large apartment building. The building is the shell. The floor is the subshell, and each room on that floor is called an orbital. And the people living in the rooms are the electrons. I think that is the better analogy to go with. Now, another very important point, can an orbital accommodate an unlimited number of electrons? The answer is no. Every orbital can hold a maximum of 2 electrons only, and those 2 electrons must have opposite spins. We'll understand why this happens when we study Pauli's exclusion principle in the next section. Yes. So far we have learned what an orbital and where an electron is likely to be found. But another question naturally arises. If an atom has many orbitals available, how do electrons decide which orbital to enter first? Do they fill randomly or do they follow certain rules? Nature follows very strict rules. There are three fundamental principles that govern the filling of electrons. Pauli's exclusion principle, Hund's rule of maximum multiplicity, and Aufbau's principle. In addition, we'll also learn the N plus L rule. So, the statement of Pauli's exclusion principle states that no two electrons in an atom can have the same set of four quantum numbers, N, L, M, S. Now, once we understand these rules, we get like the rough idea behind why which electron is holding on to one orbital. And when we are finding the orbitals, we are looking at multiple of it at the same time. The quantum number slide is gotten mixed, but it's fine. Now let's get to quantum numbers. Quantum numbers. So, in the previous section, we learned that the electrons are found in specific regions around the nucleus called orbitals. But here is an interesting question. Suppose I tell you an electron is present somewhere inside an atom. Is that information enough? Not really. Scientists wanted a way to describe an electron completely. its energy, where it's located, and the shape of its region it is occupying, its orientation, and even the direction in which it spins. To do this, they introduced quantum numbers. You can think of quantum numbers as a complete address of an electron. Just as your home address tells you exactly where you live, quantum numbers tells us exactly how to identify an electron inside an atom. There are four quantum numbers, and each one provides a different piece of information. So, let's start off with principal quantum number, or the n. The principal quantum number tells us mainly which energy level or shell the electron belongs to. It also gives us an idea about the size of the orbital and the energy of the electron. As the value of n, as you can see here, as the value of n increases, two things can happen. The electron is generally farther from the nucleus. The energy of the electron also increases. The possible values of n are positive whole numbers. So 1, 2, 3 and 4 basically. I don't think we are going to be needing anything more than that. So let's just go for that. Hold up. These correspond. So basically these n, the whole number values of n, actually natural number values 1, 2, 3 and 4 are associated with K, L, M, N shells, as I told before. The larger the value of n, the larger the shell. That is obvious. We have learned it in the lower classes. So whenever you see the number 3 in an electronic configuration like 3p, you immediately know that the electron belongs to the third shell or the M shell. Okay, this is what it is. Now let's move to the azimuthal quantum number. I still can't pronounce this guy's name. If you can't, it's not a big deal. Yes. So this is called the azimuthal quantum number, represented by the letter L. Now, while the principal quantum number tells us that the shell the azimuthal quantum number tells us which subshell the electron occupies. That one you know. Yes. So let's understand this with an example. If n is equal to 1, then L can only be 0. If n is equal to 2, L can be 0 or 1. And if n is equal to 3, L can be 0, 1 or 2. Get it? So L can have maximum L can have maximum value of n minus 1. If the value of n is given, you can find the L value. Maximum, this thing, what do you call? Maximum it will be like, see, if it is 3, it is going to be 2 or something, or less than 2 only. That much you remember. Now, I'll tell you about subshells, okay? There are basically 4 subshells, S, P, D and F. It is given here in the slide. And it determines the orbital shape and the angular momentum basically. So, whenever you see 2p, the number 2 will represent the shell, while p will represent the subshell, and that will also give you the orbital shape. And wait, hold up. I'll tell you the orbital shapes which and all is there. I don't know why it's not included in the slide, but basically the shapes of your this thing got discharged. Laptop charging on. Yes. So the shapes of the orbital are S. If it is S, the shape of the orbital is going to be spherical. It's a sphere. Okay, not a big deal. If it is a p orbital, it is going to be a cloud-like shape. Two thingies attached in circular thingies like this. Okay. And this thing. If it is D, then it is going to have a 3D orbital. The plane will go up, down, and one side into the paper and one side outside, like one outside of the paper. Okay. These are the only three I find. F orbital are sevenfold, degenerate, and yeah, there are sevenfold orientations in space. They possess very complicated shapes. So we will ignore that. Also because I might or might not have prepared for that. Yes. Okay. So let's go to the third slide, the magnetic quantum numbers. The third quantum number is the magnetic quantum number, represented as M. Okay, it is given here. This thing only. You can see it? Yes, it is visible. So basically, this is the magnetic quantum number. The third quantum number, it is represented as this thing. This quantum number tells us about the orientation of an orbital in space. In simple words, let me tell you, like it is how it is positioned. The possible values of m raises like it is from -1, 0, and +1. That's it. Now I'll tell you what it means. Okay. Basically, S is an subshell where L is equal to 0. Then only one possible value is there. That is going to be 0. That means that S subshell contains only one orbital. For a P subshell, where L is equal to 1, the possible values are -1, 0, and +1. Okay. From these three things, you only have to find out the. See, when you write a notation, right, you will have to. I shall show it to you on paint because it is good enough. I'll tell you how it is usually written. Let me take a bigger brush. See, you'll write 2p like this, right? Now, 2p will not give us the m value. To write the m value with this, where is the goddamn course? Yes, it will be divided into 3 blocks basically. Because one block can occupy a maximum of 2 electrons. Okay, so this will be -1, 0, +1, x, y, z. Okay, these are the 3 things. Now, when you write 2p, you will have, for example, these people have given -1 as the value of m. So the automatic base value that p will get will be x. You'll not write this one, you'll write this thingy for some reason. It is the notation, I believe. So this will be what you have to be writing. Okay, understood? Boom. Don't say it. Next part. So I'll tell you what this means, okay? It means P subshell contains 3 orbitals. Similarly, D shell will contain 5 orbitals, F shell will contain 7 orbitals. See, it is not a big thing, okay? It is basically, first shell, how many electrons will it have? 2. We have to basically take the shell you are taking and then minus the sum of all the previous shells. Like K, L, M, N. The K shell has 2 electrons. The L shell has 8 electrons. So 8 electrons it will change to 6. 8 minus 2. Similarly, this thing, third shell, M shell has 18 electrons. 18 minus 6 plus 2, which will be 8. No, 18 minus 8, which will give us 10. And then since one block can have only 2 electrons, the number that the third shell will have is 5. Then you are going to subtract, which one? 32. 32 minus 18, the one before that, you are going to subtract it and you are going to get 14. And then since you have to divide each the electrons into two groups or blocks, you will have 14. Instead of 14, you are going to have 7 orbitals. Basically divided by 2. Minus the previous one, divided off by 2. You'll get the number of orbitals. This is why P subshell can hold 6 electrons because it has 3 orbitals and each orbital can accommodate 2 electrons. Okay. Now, finally we can come to the fourth quantum number, spin quantum number. this thingy is called spin quantum number because it will be either plus half or minus half. It will determine in which direction it is spinning. Okay. Electrons behave as though they're spinning about their own axis. Although this isn't literal spinning like a ball, but we use it as a useful model. An electron can have only two possible spin orientations. Minus half represented by an upward arrow and plus half represented by an upward arrow and minus half represented by a downward arrow. Whenever two electrons they apply the same orbital, they have opposite spins. Opposite spin. One electron will have plus half while the other will have minus half. This this thing becomes extremely important when we study this Pauli's exclusion principle. Okay, bro. So let's move ahead. Let me give you a summary of all these quantum numbers. Okay. Basically, principal quantum number n tells us the Shelf energy level. The azimuthal quantum number L, it tells us, you know what, screw it, just read through this, take a screenshot or something. Now, next we are going to be going to a different topic, which is, see, if every electron has a unique set of quantum numbers, two electrons, this thing, can two electrons have more than, can two electrons have the same quantum numbers? No, not really. Actually, not at all. This is what this Pauli's exclusion principle should explain, no? This only Mr. Pauli doing. So the statement is given here, I read it out before. No two electrons in an atom can have the same set of four quantum numbers. Understood? So till now, we learned about four quantum numbers. We discovered that every electron inside an atom can be uniquely identified using these four quantum numbers. Now this immediately raises an interesting question if you think about it. If electrons are simply tiny particles, can two of them have exactly the same set of four quantum numbers? Or in simple words, can two electrons become completely identical inside an atom? See, the thing is no. And this is what this guy is explaining. I think his name was Wolfgang Pauli. He sounds so German. I should not be racist. Yes. His works, this guy, no, he's really important. I think he must have gotten some Nobel Prize also. We'll check. We'll check. What are we doing? Pucho. Did Wolfgang Pauli get Nobel Prize? Yes, this guy got Nobel Prize. Very interesting. Why did we do this? Utterly useless. Okay, but this guy is important for some great reason. So the Pauli exclusion principle completely changes our understanding of how electrons are arranged inside an atom. So first I have already told the official statement. So we know the four quantum numbers, N, N, L, M, and this thing, spin quantum number, M and S. We'll take it separately. These people usually give M, L, and MS. We'll take it as M and S separately. No, yeah, we'll take it as M and S separately. Screw them. So every electron has four quantum numbers, and each electron carries this shit like how we have an ID card like that. Okay. For two electrons, it cannot be completely identical. All four values would have to match exactly for it to be exactly same. Okay. Nature does not allow that. If three quantum numbers are the same, the fourth must be different. Because even in your school, ID cards cannot be the same for two people, no? Like that only it is. Now, let me apply this principle to an orbital. Suppose we have one empty orbital. Can we place an electron inside it? Of course we can. Can we place a second electron? Yes, but there's an important condition. The second electron must have the opposite spin. Okay? It should be up arrow or down arrow. Hmm? Yes, you picture it, you better do it. The first electron may have a spin of plus half, represented by an upward arrow. I'll plug this off in the charger. Wait, keep it off 10 seconds or something. I don't know. So, what if we try placing both electrons with the same spin? Okay? Two upward arrows. It is not allowed. Why, if you ask, means? Because two electrons will have the exact same value. All four quantum numbers become identical. It is going to be not possible because this guy said so. Yes, he must have done something. Nobody says such things simply. So, according to the Pauli exclusion principle, the situation is completely impossible. Now, let me tell you with a simple analogy. I love using analogies, yes. Imagine an examination hall, your trauma place. Every student has a unique roll number. Even if two students are sitting in the same classroom, they cannot have the same roll numbers. Similarly, every electron inside an atom must have its own unique identity. Two electrons may occupy the same orbital, but they cannot have identical quantum numbers. The only way both electrons can stay together is by having opposite spins. Now, we can answer another important question. Okay. Where is that slide? Yes. We can answer another important question. How many electrons can fit inside one orbital? The answer is exactly true. No 3, no 4. 2. See, it is because two spin values exist. Once both are occupied, there is no third possible spin available. Therefore, no additional electron can enter the orbital. Now, let me tell you, okay, if s orbital is there, this maximum 2 electrons only, no. P subshell will have 3 things, I told you that time. D subshell will have 10 electrons, so it is going to have 5 orbitals. Only 2 things it will occupy maximum, because 2 charges, like plus half and minus half it will be. So in one block or one orbital, only 2 electrons can exist. So just find the value of electrons present, maximum electrons present, and this divided by 2. So you'll get the number of orbitals. So I've gotten bored. So that's it for today, guys. Thank you for watching the video, and the rest of the topic is going to be covered in the next video. Thank you.